Okay, we're about to begin the chapter on thermochemistry. And up to this point in the course, this is the first time we're going to analyze energy transfer processes that occur during chemical reactions. In this chapter, we're going to apply the first law of thermodynamics to chemical reactions. The second law of thermodynamics we'll be discussing later in a separate chapter. And so in this video, what I want to do is I want to show how the first law is applied in general chemistry. In other words, how do we use the first law of thermodynamics in this course to analyze chemical processes? So, okay, here is the first law of thermodynamics. And this is the completely general first law. This is as general as it gets. So we've got some completely arbitrarily shaped control volume here with an arbitrarily shaped control surface. So the system here, you can think about it's arbitrarily shaped and it has no constraints. Okay, so now with this system here defined, we can apply the first law of thermodynamics to this system, to where the first law is given by this equation here, this single equation here, which is just an energy balance equation. On the left side is all the ways that the energy content contained within the system, within this control volume, can change. And then on the right side are all of the ways that energy can be transferred across the control surface. So all of the ways that energy can be transferred into the system or out of the system. However, when we apply the first law to chemical reactions in general chemistry, many of these terms are going to be zero. And then furthermore, the system isn't going to be just completely general in terms of it has no constraints applied. And in some cases, it won't be just arbitrarily shaped either. So therefore, the goal of this video is to understand the general first law and then clearly see how this all simplifies in the context of chemical reactions. Okay, so we want to start off by understanding exactly how the first law works, the general first law. So how exactly does what's shown here work? Well, okay, the first law of thermodynamics is a statement of the conservation of energy. When you hear phrases such as energy is conserved or conservation of energy, those statements are in reference to the first law of thermodynamics. And so the first law exists because of the fact that energy cannot be created or destroyed. Energy can change forms, but it can't just spontaneously appear or disappear. And so one useful way to think about the first law is from the perspective of accounting, right? So like the books must always balance. Money can't just appear out of nowhere or disappear. It can change forms, but money can't just be created or destroyed. The books must always balance, right? So in financial accounting, all the money entering and leaving a bank account can be tracked. Again, money doesn't simply appear or disappear. It can change form, but it can't just appear or disappear. So, for example, you might spend money to purchase an asset, such as a vehicle. In that case, money changes forms. Cash is converted into property or equity. Alternatively, it might seem like some money appeared in your account out of nowhere, so it wasn't deposited as a paycheck. You didn't do any work. It seems to just have appeared out of nowhere. Well, in that case, it was borrowed. So the money has the form of a debt, a liability. Okay, and so again, the first law of thermodynamics works in a similar way, except that instead of tracking money, we're tracking energy. The first law states that the change in the total energy content contained within the system equals the energy that has entered the system minus the energy that has left the system. So this is like over some time period. Over some time period, delta T, the change in the total energy content that's contained within the system is equal to the energy that was transferred into the system over that time period, over that delta T, minus the energy that was transferred out of the system over that same time period. Again, this is similar to a bank account. So where the change in the account balance equals money deposited minus money withdrawn. Okay, and so the important point is that energy can exist in many different forms. Energy can be transferred into or out of the system in different ways, in different forms. And the energy contained within the system, the energy content contained within the system can have different forms. However, regardless of the forms involved, the overall energy balance must always hold. This equation can never be violated. The first law must be satisfied in all circumstances, in every physical situation. Because if the first law is violated, then that's implying that energy has been created or destroyed, which contradicts a fundamental law of nature. Okay, and so to apply the first law to any problem, the first step is to define the system. You can't apply this equation here by itself. This equation, the first law equation by itself, doesn't make sense. So just this here as it sits doesn't make sense because you're applying the first law to some system. So now this makes sense because we're doing the first law energy balance with respect to this system. Okay, so now, but the idea of a system is not unique to thermodynamics. In science and engineering in general, whenever you analyze a problem, you begin by specifying what portion of the universe you're studying. And that portion of the universe is what's called the system, and everything else is called the surroundings. Okay, and so to define the system, we also define the system boundary, which is the surface that separates the system from its surroundings. And the boundary can be absolutely anything you want. You can define a system to be absolutely whatever you want it to be. Systems are very flexible. It's completely up to the scientist, the physicist, the engineer, etc. Again, when defining a system, all you're doing is you're just isolating a portion of the universe from the rest of the universe for the purposes of analyzing that portion of the universe. And so, okay, the system boundary can be like a real physical surface, the walls of a container, for example, or an imaginary surface drawn around a region of space. Most systems are going to enclose some three-dimensional region of space, and therefore the system's going to have some volume to it. For example, the gas inside of a container, the reacting chemicals inside of a flask. However, again, this concept is extremely flexible. In principle, a system could even be defined as a two-dimensional surface, like the surface of a window, or even like an effectively one-dimensional region, such as heat flowing through a thin wire. So you're just isolating the very thin, effectively one-dimensional wire for analysis from the rest of the universe. And so the key idea is simply that we choose a portion of the universe and place a boundary around it for analysis. Okay, and so now can a system or a system boundary move or change shape? And the answer is yes, absolutely. A system boundary can be fixed, moving, expanding, contracting, or deforming, just depending on how the system is defined. So consider a piston cylinder. If we define the system to be, we're isolating the gas body that's contained inside of this cylinder, then in that case, we could just define the system boundaries to be the inner walls of the cylinder and the inner face of the piston. And so in this case, because of the way the system is defined, to where one portion of the system boundary is fixed to a face that can move, that's the piston face. Well, if the piston moves, this boundary is going to move with it, this boundary of the control volume, which means the control volume is going to change shape. The entire volume is going to change. When the piston moves up, the control volume is going to expand. When the piston moves down, the control volume is going to contract. And so the entire system, based on the way it's defined, again, it can expand, contract, deform. It can move or accelerate together as like a rigid body. For example, if you think about the piston cylinders inside of a vehicle, well, the entire piston, the entire interior of the cylinder, and everything that's contained within the cylinder, all the gas contained within the cylinder, is moving together as a rigid body. This is all perfectly acceptable as far as defining a system and the resulting behavior of the system boundaries and like the entire control volume. The only requirement is that the system must be clearly defined based on exactly what you define the system to be is what's going to dictate exactly how the system behaves over time, if the system expands or contracts or if it moves. So when defining a system, you need to specify what matter, what mass is included in the system. This might change over time. You have to define the nature of the system, starting at time t0 and all the way to the final time. Where are the system boundaries located? So are the boundaries fixed or attached to some surfaces? And can those surfaces move? Can the entire control volume, can the entire surface move together as a unit? Can the control volume deform, expand, contract, change shape? Okay, and so once the system is defined, then we can apply the first law to that system. Okay, and so, but again, though, defining a system is not something that's just unique to the first law or even to thermodynamics. No, we define systems in all of science, physics, and engineering. So with this system defined here, for example, we can apply the first law of thermodynamics to this system, or we could apply the second law of thermodynamics to this system, which we're going to do in a later chapter in this course. We could apply the law of conservation of mass, or the conservation of linear momentum, conservation of charge, or even not even a conservation law. You could do a heat transfer analysis or an equation of state, the ideal gas law. If this system here is defined to contain a gas body, then you can apply the ideal gas law to that system or one of the modified forms of the ideal gas law. Okay, however, in this video, we're focusing specifically on the first law of thermodynamics. So where, again, the first law states that the change in energy contained within a system over a time interval equals the total energy transferred into the system minus the total energy transferred out of the system over that same time interval. Okay, and so now in a general chemistry course, what is the system going to be most of the time? Well, okay, in most cases, in the vast majority of cases, the system corresponds to the chemical reaction itself. And so more specifically, we think about an imaginary boundary that encloses all of the reacting substances. So all of the reactants and all of the products before, during, and after the reaction. So before the reaction begins, the system boundary encloses all of the reactants. And then during the reaction, the boundary encloses both reactants and products. And then after the reaction completes, the boundary encloses all of the products. So the system, when we're analyzing just like a general chemical reaction, the system consists of all matter participating in the chemical reaction. So for example, let's consider the reaction between ammonia gas and hydrogen chloride gas to produce solid ammonium chloride. Okay, so before the reaction occurs, the system contains all of the ammonia and hydrogen chloride gas. So the system encloses the entire ammonia gas body and the entire hydrogen chloride gas body. Okay, so let's suppose that this vessel here contains just pure ammonia gas, and this vessel here contains pure hydrogen chloride gas. Okay, so at this moment, before the reaction occurs, before these two gases are mixed, what would be the system boundary? Well, again, the system is defined to enclose all of the reactants and products involved in the reaction. So in this case, the system would enclose all of the ammonia and all of the hydrogen chloride gas. Okay, so do we sort of think about these two separate control volumes with two separate system boundaries defined by the inner walls of these two vessels? Well, you could do that, but in classical thermodynamics, the way we'll be working with thermodynamics in this course, you only want to be dealing with one single system boundary, one single enclosure, because otherwise the energy balance equations get a little more complicated. So at this stage, the boundary would look something like this. It would just be the smallest possible single boundary that encloses both gas bodies. Okay, but for the actual chemical reaction, we're really more thinking about it this way. So you have one container, and we have the two gases mixed. And we start off by thinking about, so here, this would be the instant in which these two gases are mixed, in the sense that no reaction has occurred yet. Not one molecule of ammonia has reacted with a molecule of hydrogen chloride. The instantaneous moment right when these gases are mixed. But then, like nanoseconds later, after this moment, the reaction is going to start. Okay, so at this moment, where you just have the reactants, the ammonia and the hydrogen chloride gas, at this moment, the boundary surface, the boundary that encloses this entire chemical reaction, where at this step it's just the reactants, is the inner walls of the vessel. Okay, and then now, but as the reaction proceeds, what results is you have solid ammonium chloride forming out of the gas. Okay, but as long as there's still some reactant gas present, so you've got some ammonium chloride coming out, but as long as there's still some reactant gas present, so the reaction hasn't gone all the way to completion, then the system boundary doesn't change. It'll still just be the inner walls of the container walls of the gas, because as long as there's some reactant present, you still have a gas body in this vessel. So to enclose that entire gas body, we know that gases take up the entire volume of their container. The control volume needs to be the entire inner walls of the container. And this works completely fine in the sense that this boundary, the inner walls of the container, also enclose the products as well. Now, okay, once the reaction is fully complete, what happens to the system boundary? And so let's assume that the amounts of the reactant gases are stoichiometric. So there's no limiting reagent or excess reagent. So once this reaction goes to completion, there's no gas left. You're just left with pure ammonium chloride. So in that case, when the reaction is complete, is the system boundary still the walls of the container, the inner walls of the container? Well, no, it's not, because there's no gas left in the container. So what would happen is, what you would be left with is just all of this ammonium chloride that's settled to the bottom. So at this point, if we think about the definition of the system just, it's going to enclose, isolate from the universe any reactants and or products associated with this chemical reaction. Well, at this point, the boundary being the inner walls of the container would be unnecessary. This would be the new boundary. So going from reactants to products, the volume of the system for this reaction is going to shrink significantly. Okay, and so again, a system is absolutely allowed to expand, contract, change shape, move, accelerate. The system will do whatever it needs to do to conform to the exact specifications of how it's defined. That's the idea. And so to give another example of a system enclosing a solid or solid particles, if you had a system defined to be such that it encloses this pile of graphite particles, what would the system boundary be? Well, again, in classical thermodynamics, we don't think about two or more distinct system volumes. It's like a little volume enclosing every particle. No. In this case, the system would just be some single boundary that hugs all of these particles as a unit as tightly as possible. That's it. Okay, so now let's look at a different example, a hydrogen displacement reaction. All right, so solid zinc reacts with hydrochloric acid to produce aqueous zinc chloride and hydrogen gas, H2 gas. Okay, so suppose we drop a piece of solid zinc into a beaker that contains a hydrochloric acid solution. Okay, so this is the instant before the reaction begins. Within nanoseconds, that this reaction is going to start. But right here, you just have pure hydrochloric acid solution and pure solid zinc submersed. At this moment, what is the system? Okay, well, in principle, we could specify the system, define the system to be ignoring the H2O solvent to where it would be sort of strictly just enclosing all of the H plus and the Cl minus ions. But instead, it's more practical to define the system as all of the reacting material inside of the flask, inside of the container. Okay, so this is a reaction between solid zinc and hydrochloric acid, or aqueous hydrogen chloride. Well, aqueous hydrogen chloride, in principle, is not just the dissolved H plus and Cl minus ions, but the solvent as well, right? So in this case, it's more practical to think about the system boundary as the inner walls of the container, in that it encloses the entire solution. So the inner walls of the container and the surface of the water, to where now the system encloses the entire solution and the solid zinc. Okay, so now let's think about what happens as the reaction proceeds forward. So when the reaction completes, has the system changed shape or size relative to how it started? Well, yes, absolutely. Because during the reaction, hydrogen gas is produced, to where a lot of this gas is going to form bubbles that are going to escape from the solution. You're going to have hydrogen gas coming out. Okay, and so if the system is defined for this chemical reaction to be that it contains all of the reactants and all of the products at any time, well, then the system boundary is going to need to expand to include the final solution that's left over, as well as this hydrogen gas body. So this is going to need to be the system after the reaction has gone to completion. So overall, going from reactants to products for this chemical reaction, the system expands. Okay, but now thinking about how we can define a system to be absolutely whatever we want, let's think about, what if we defined the system to be to where it contains only the solution? The system strictly encloses the solution in the beaker, so the inner walls of the container and the surface of the liquid. So the system is constrained. It always contains the inner walls of the beaker, but this surface is fixed to the surface of the liquid. Okay, so in that case, what's the system when the reaction has gone to completion? Well, based on the definition, it's still just enclosing the solution. This surface, this portion of the boundary surface, is fixed to the liquid surface. All right, so in this case, when the hydrogen escapes from the surface of the solution, it's going to be crossing the boundary surface, the control surface. So the way we define the system determines what crosses the boundary and what remains inside. Okay, and so but mass is allowed to cross a system boundary. So in that case, would this count as energy crossing the system boundary with respect to the first law? Okay, so if we come back here to the general first law, again, once you've defined a system and a corresponding control surface, so you've got your control surface and your control volume defined, then you can apply the first law to that system to where, again, the first law is simply an energy balance with respect to the control volume given by this single equation shown here. And so the idea is over some time interval delta t, you can choose any time interval you want. For any time interval whatsoever, this equation must hold. But over this time interval, the left side of the equation represents the total change in energy contained within the system. And the right side represents the total amount of energy that has been transferred to the system across the system boundary minus the total amount of energy that has been transferred from the system across the system boundary. Okay, and so this can be a little confusing at first when you first learn this. Let's think about the left side of this equation first. All right, so the time interval delta t is given by some time t2 minus some time t1, right? And so the idea is that at time t1 and time t2, or at any moment we want, we can take a snapshot, take a picture of the system at that particular instant in time. So let's think about this idea using the bank account analogy. So here's the balance in the bank account. You have delta t. Okay, so you can take a snapshot of a bank account, a picture, at any moment in time. For example, at time t1 and at time t2, you take a picture of the bank account. And at these times, in these pictures, there's going to be some account balance, right? Some single number, one number that has units of dollars. And to determine the total balance, to determine the details of where that total balance comes from, you can look at that picture, you can look at the account and add up all of the money in the account. And that money can exist in different forms, different types of purchases, etc. But all of those different quantities, all of those different forms still share the same unit. They're still all in units of dollars, which is why you can add them. Remember, you're not allowed to add quantities unless they have the same units. So you can add them all together and get this one single final number. Again, we're thinking about it at a moment in time, at some time t1 or t2 or whatever. You get this single final number in dollars. Okay, so suppose you do this at time t1, you get some dollar amount, some single number, some single account balance, and you also do this at time t2. You get some other dollar amount, this single number. Well, the change in the account balance over the time interval delta t is simply the balance at time t2 minus the balance at time t1. Okay, and so it's the exact same idea with the first law. These terms here represent different forms of energy that can be contained within the system. These are all of the different forms of energy that can be contained within the system. This is the completely general first law of thermodynamics. So inside of a system, as far as energy, the types of energy that can be contained inside of a system are, you could have bulk kinetic energy, bulk potential energy, or internal energy. That's it. To where the delta is just corresponding to the changes in these types of energy. The change in the total bulk kinetic energy, the change in the total bulk potential energy, the change in the total internal energy over this delta t, going from time t2 to t1, or going from time t1 to t2. So at time t1, you take a picture, you add up all of the energies contained within the system that fall under the category of this is internal energy. Then you go to the picture for time t2, and you add up all of the energy content that is internal energy. Subtract the internal energy at time t2 minus the internal energy at time t1. That's delta U. Do the same thing with with the bulk potential energy, the change in bulk potential energy, and the change in the bulk kinetic energy. Add up all of these changes, and you get the total change in the energy content balance within the system going from time T1 to time T2. Okay, but you're allowed to add all of these energies because that they all have the same units, that they're all energies. Just like with the account balance, that everything is in units of dollars. That's why at any given moment in time, at any given snapshot, you can add up all of these different forms of energy, combine them all together, and get one single total energy content value contained within the system. Remember from the previous video, energy, and no matter what form it's in, all energy has the same units, the same dimensions. Energy is a mass times a length squared divided by a time squared. Okay, now the right side of the equation represents the total amount of energy transferred to or from the system across the control surface during the time delta t, over the time delta t. Okay, again, this is just like the bank account analogy. There's different ways that you can transfer money to or from a bank account. There's different forms of money transfers. But again, just like with the account balance, all of the different types of transfers are still just transfers of money, no matter what the form. Any type of transfer you can trace back to some dollar amount. And just because over some time interval, delta t, let's say the account balance doesn't change. So the final account balance at time t2 minus the final account balance at time t1, let's say is 0. This doesn't mean that transfers to or from the bank account didn't occur during that time interval. Of course they could have occurred. It could simply be that you deposited exactly as much money as you spent during that time interval. Okay, and so it's the exact same idea with respect to the first law. There's different ways that you can transfer energy across the control surface, transfer energy into or out of the control volume. Okay, but no matter what the case, no matter what the form, you're always transferring energy. These all have the same units, the dimension of a mass times a length squared divided by time squared. And just because over some time delta t, the total amount of energy contained within the system doesn't change, that doesn't mean that there weren't energy transfers taking place during that time delta t. Because it could absolutely be the case that over the time delta t, the amount of energy that was transferred into the control volume was the same amount of energy that was transferred out of the control volume. Okay, and so again, this is the completely general first law. We talked about all the ways that energy can be contained within the system. Now, here are all of the ways that energy can be transferred to or from the system, into or out of the system. All the ways that energy can be transferred across the control surface. So energy can be transferred across a control surface through heat, work, or mass transfer. Okay, and so we were talking about the hydrogen displacement reaction and the idea of what if we decided to define the system boundary to where it strictly enclosed the aqueous solution. For this entire reaction, the system boundary was defined such that it always enclosed just the aqueous solution. Well, first of all, that wouldn't be very practical for analyzing the chemical reaction, which is why we're typically not going to define the system boundary for a chemical reaction this way. It's going to be defined based on the system always encloses all of the reactants and products. But I'm just trying to give you an intuitive feel for how systems and the first law work and how exactly they're applied to analyze chemical reactions. And so again, but if the system were defined this way, to where it strictly for the entire reaction encloses just the aqueous solution, then as we talked about, you would have hydrogen gas, H2 gas particles, crossing the system boundary, this portion of the system boundary. And so like we just talked about, with respect to the first law, mass crossing the control surface, the H2 gas in this case, does correspond to a form of energy transfer across the control surface, either into or out of the system, depending on if the mass is entering or leaving. So therefore, With the system defined this way, these mass transfer terms wouldn't be zero because, again, H2 gas would be leaving the system across the control surface. Okay, but now this can be confusing at first when you first learn this, because how is mass entering or leaving the system considered energy transfer? Because mass isn't energy, right? Yes, there's Einstein's famous equation, E is equal to mc squared, which tells us that at a deep level, mass and energy are equivalent in some sense. But in the classical scientific analysis we perform, for example, in general chemistry or classical thermodynamics, we don't treat mass itself as energy in that sense. In other words, if we strictly just added a pool ball into this control volume, but it was motionless, well, adding a motionless mass to the control volume shouldn't change the energy content contained within the control volume, should it? Okay, well, actually, adding or removing a motionless mass like this to the system would correspond to an energy transfer to or from the system. This would here increase the energy content contained within the system. Again, I'm saying, but this is motionless. Obviously, if this were in motion, then you would say, okay, well, 1/2 mv squared, it has a kinetic energy, but even with if this has no bulk kinetic energy, the entire pool ball has no velocity, this still, as it sits motionless, is adding energy to this system. And so this energy appears primarily in the form of internal energy. So if we take a picture at time t2, we add up all the energy, get a final value, and then we just add this motionless pool ball to the system. Well, the addition of the pool ball is going to increase the U value at time t2, the capital U value. And the reason is because a mass like this, any mass, contains thermal energy, right? Meaning the random kinetic motion of the atoms or molecules within the material. This is the energy directly associated with the temperature reading of a substance. So when mass enters or leaves a system, thermal energy enters or leaves the system as well. Now, but the mass is also going to contain a chemical potential energy. For example, if you added gasoline to this system, well, you'd be adding chemical energy to that system. Okay, but now this can still be confusing because, okay, so suppose instead we throw this pool ball into the system, into the control volume. So now the pool ball is in motion. It's bouncing off the walls and it's in constant motion. Okay, so the pool ball contains thermal energy and chemical potential energy. So those forms of internal energy have been added to the system. That's fine. But what about the kinetic energy of the pool ball? It's not the kinetic energies of the random kinetic energies of the atoms that make up the pool ball. No, the bulk kinetic energy of the entire pool ball as a unit. And perhaps it also has a bulk potential energy. Maybe there's some apparatus in here so the pool ball can go up relative to gravity. Okay, well, yes, obviously those forms of energy have also been added to the system in addition to the thermal energy and the chemical potential energy. So whatever the velocity of the pool ball is, you take 1/2 times the mass of the ball times its velocity squared. That bulk kinetic energy has also been added to the system. Okay, and so those bulk energies would be associated with these bulk energies here, the bulk kinetic energy and the bulk potential energy, right? Well, this is actually not the case, and this is where things can get a little confusing. So with respect to the first law energy balance, the bulk kinetic and potential energies of the pool ball would be also thought of as adding to the total internal energy content of the system. Now, this is confusing because the uniform unison motion of a pool ball in and of itself is absolutely not internal energy, right? That's not thermal energy or chemical potential energy. And yes, that's true. But with respect to a first law energy balance corresponding to some system, the bulk kinetic energies and potential energies of objects contained within the system is accounted for as part of the system's internal energy, because these energies are internal to the system. Again, I am not saying at all that the bulk kinetic energy of this pool ball, or the bulk potential energy of this pool ball, or there could be multiple pool balls, or multiple bulk motions or potential energies, or of whatever objects within this system. I'm not saying that these energies in and of themselves are internal energies, which we really think of as corresponding to thermal energies and chemical potential energies of mass. I'm just saying that with respect to a first law energy balance, that's with respect to some system, the bulk kinetic and potential energies of these pool balls, or of whatever kind of mass, whatever kind of bulk kinetic or potential energy contained within the system, is grouped in with this potential energy term. Okay, so why though? Well, the reason is because these bulk kinetic and potential energies here in the first law equation are referring only to motion of the system's center of mass, right? Let's say here's the center of mass. So this is in reference to the bulk kinetic and potential energy of the entire system and everything contained within the system as a unit. For example, if the center of mass of the entire system had some velocity, v, and this is at some moment in time, some snapshot at like t2 or t1 or whatever, then at that moment, the bulk kinetic energy of the entire system, so let's say at time t2, for example, if this is at time t2, is 1/2 times the mass of the entire system, the mass, the total mass of everything contained within the system, times the velocity of the center of mass, this v squared. And the same exact idea applies to the bulk potential energy of the entire system. These energies are associated with the motion or position of the system as a whole. And so, to better understand this idea, let's go back to the piston cylinder example. So let's say that this piston cylinder is inside of a vehicle. This is one of the piston cylinders inside of an engine, and this vehicle is in motion. Okay, and so the system is defined such that it contains all of the mass, all of the gas vapor that's inside of the cylinder. Therefore, the system boundary is just the inner walls of the cylinder and the interface of the piston. And so if we want to calculate at some time, T2, T1, whatever, some moment in time, some picture, at some snapshot, if we want to calculate the total energy that's contained within this system, well, part of that energy will be the thermal energy of the gas, of the vapor, so that the random kinetic energy of motion of all the gas particles. Part of this energy will be the chemical potential energy of the gas vapor. And so this thermal and chemical potential energy will be contained within this internal energy category. But if the entire system is also moving with some velocity, then the idea is that all of the mass contained within the system, every single vapor particle, is moving in unison together in the same direction with the same exact velocity magnitude. So I'm not referring to the thermal energy of the particles here. That's separate. The random kinetic energies all over the place. No, the vehicle is moving with a certain velocity. So in that sense, this entire system is moving in unison with a certain velocity, which you can look at from the perspective of every single one of these gas particles is moving with the exact same velocity in terms of magnitude and direction. Okay, and so if at this moment in time you're trying to account for this bulk kinetic energy, this bulk movement in unison of every single particle within the system, well, all you need to do is you don't have to go and add the kinetic energies of every single particle. Instead, you can just take the sum total of the masses of all of the particles within the system, which is the mass of the system, and then multiply this by the velocity of the center of mass, the magnitude of the velocity of the center of mass of the entire system squared. And then times 1/2. And this accounts for the sum total of all of the kinetic energies, the in unison kinetic energies of all the particles within the system. You see? And it's the same exact idea with respect to bulk potential energy. If the entire system changes position relative to, let's say, a gravitational field, well, then every single particle was moved a certain distance against that gravitational field. So you could just calculate the bulk potential energy of every single particle within the system with respect to the center of mass of the system. Now, what about heat transfer and work? What does it mean to say that energy can be transferred into or out of a system across a control surface via heat or work? So let's start with heat transfer. When we say that heat crosses a system boundary, what exactly does that mean? Well, there's actually an entire field of study called heat transfer that focuses on this topic in detail. But you're probably already familiar with the basic mechanisms. So heat can be transferred by conduction, convection, or radiation, to where heat transfer is always the result of a temperature difference. Without a temperature gradient, there is no heat transfer. Okay, but let's clarify what heat actually is. So heat is simply the transfer of thermal energy. You might hear the phrase, okay, this system contains a certain amount of heat. That's technically not the correct terminology. The correct terminology would be that the system contains a certain amount of thermal energy at this moment in time. The term heat is really in reference to the transfer of thermal energy. Heat is a energy transfer term. Okay, and so again, thermal energy, remember, is, if we think back to kinetic molecular theory, we saw that the temperature of a gas is proportional to the average kinetic energy of the gas particles. The molecules of a gas are constantly moving in random directions, colliding with each other and with the walls of the container. And it's this random microscopic motion is what we call thermal energy. But the same basic idea applies to liquids and solids. The atoms and molecules in a liquid or solid are also in constant motion, vibrating, rotating, and interacting with one another. And the temperature of the substance reflects the average kinetic energy of these microscopic motions. So when heat transfer occurs, what's really happening is that thermal energy is being transferred from one place to another. That transfer can occur between two different bodies or between different regions of the same body, solid, liquid, or gas body. And it occurs through the mechanisms of conduction, convection, or radiation. Okay, but now, with respect to the first law, any heat transfer that's taking place strictly within the system or strictly outside of the system is not going to appear in the first law equation, in the first law balance. Okay, because this term, this heat transfer term, is only in reference to heat transfer that's occurring across the control surface, either into or out of the system. So if heat enters the system, then Q is positive. If heat leaves the system, then Q is negative. Now, note that you can have multiple different heat transfer processes occurring over the same time delta T. This is just an all-encompassing term saying over the time delta T, add up all of the heat transfers, even if there's multiple different heat transfers that took place across the control surface over the time delta T. So you do the sum total. So you add any Qs going across the surface into the system, and you subtract any Qs going across the surface out of the system, and that's Q. Okay, now what type of energy content within the system is affected by heat transfer? So in general, heat transfer is going to affect the internal energy content within the system. Heat transfer can also indirectly lead to work interactions. So, for example, in an internal combustion engine, the heat released through the combustion of the gas vapor, gasoline vapor, increases the thermal energy significantly of the gas, which increases the gas pressure. And that pressure then pushes on and moves the piston face, which is a form of work. So energy can ultimately be converted between different forms. Thermal energy can be converted into mechanical energy, electrical energy, and other forms depending on the physical processes taking place. However, the fundamental nature of heat transfer itself is the transfer of thermal energy, to where thermal energy is associated with the microscopic random motion of particles. And this type of energy falls under the category of internal energy. All right, so now what about work? What is work? Well, in the previous video, talking about what is energy, we talked about how energy can be viewed from two different perspectives. One perspective is the kinetic and potential energy perspective, and the other perspective is the force acting over a distance perspective, right? Because again, the dimensions of energy is a mass times a length squared divided by a time squared. All energy, no matter what form, all energy in the universe is fundamentally a mass times a length squared divided by a time squared. Okay, so one form that you can put this in is you can say that this is a mass times a velocity. So mass times a length per time is a velocity squared. So there's the kinetic energy perspective, right? So these are the same because all you've done here is just you've applied the exponent to get mass times length squared per time squared. But then you could also write this as a force. So if we think of mass times acceleration, so mass times length per time squared, this is the units of force. And then, but now we're left with just a distance. So this is a force times a distance. So here's the kinetic energy perspective, and here's the work or the potential energy perspective as well. Potential energy is you think about in a lot of cases moving a force over a distance. When I think potential energy, I think stored kinetic energy. So here's the kinetic energy, potential energy perspective, and then here's the work perspective, a force times a distance. But that's kind of confusing because you think gravitational potential energy, you're moving something a certain distance against like the force of gravity. That's gravitational potential energy. Like chemical potential energy, you're moving a mass. You're bringing, let's say, like a chemical elements, chemical atoms together. You're applying a force to push these molecules, these particles together over a distance. So you get a chemical potential energy. So, but again, you can take the dimensions of energy and you could put it into this kinetic energy perspective or this force times distance perspective. And this is the work perspective. Work is energy in the form of a force applied over a distance, force times distance. Work is energy transferred when a force acts through a displacement. Okay, so now, just like with heat, when it comes to the first law energy balance, we're not concerned with any work that takes place strictly within the system or strictly outside of the system. We're only concerned with work that takes place at the system boundary, across the system boundary, either into or out of the system. Okay, and so in order for work to be transferred across a system boundary, two things must happen. So first, a force must act at the system boundary. The point of application of the force has to be on the system boundary, and that point of application must move with the force and with the system boundary. So the system boundary is going to have to move. There's no way that work can act on a system boundary if the system boundary is not moving. All right. And so we've talked about how there's two ways that a system boundary can move. A system boundary can move due to the deformation of the system. The system expands or it shrinks or it just deforms. Or the system could not be expanding or contracting or deforming. It could be moving as a rigid body. That's two ways that the boundary of a system can move. So let's think about the rigid body movement scenario. So in that case, let's say that this system, the boundaries of this system are completely rigid. So this is not going to expand, contract, or deform in any way, but the system can move as a rigid body. The center of mass can move. Well, okay, if the point of application of this force is on the system boundary, and as the system moves, this point of application stays on the system boundary along with the force, then work is being done by this force on the system. Now, is this work being transferred to the system or is it being taken out of the system? So is work being transferred into the system or out of the system? Well, that just depends on the direction of the force relative to the direction of the motion. In this case, the direction of the force is somewhat in line with the direction of the motion. So if the force is in line with the displacement, then that's work being transferred to the system. If the force is opposing the direction of the displacement, then that's work being transferred from the system. Now, note, though, that so in this case, to get the work transferred to the system, we wouldn't just multiply the magnitude of the force by the magnitude of the velocity. We would strictly need to multiply the magnitude of the force by the amount of displacement in the direction of the force. So you would do that with this force as a vector and this velocity as a vector, you would just take the dot product between this force vector and this velocity vector. So work is you take the magnitude of the force times the displacement in along the line of action of the force. So if you have some particle moving in this direction, a displacement in this direction, and a force acting perpendicular to that displacement, then no work is done on this particle by this force. But then from the other perspective, if you do have a force acting along this direction of displacement, but the magnitude of the force is zero, so which means there's no force, then no work is done from that perspective as well. Okay, and so what energy content within the system is work most closely associated with? If work is transferred to a system or from a system, what kind of energy content is that work adding to or removing from the system, at least directly? Well, that's going to be the bulk kinetic and potential energies. If you have a shoebox, for example, and you apply a force to that shoebox and now you're putting it in motion, what are you doing? How have you changed the energy content within the shoebox? Well, now all of the air particles have this unison kinetic energy. They're all moving in unison with this velocity. Or same idea if you picked up a shoebox with a bunch of stuff in it and put it on a table. Well, the work due to the force has added a gravitational potential energy to the contents within the shoebox. All of the contents as a whole, as a unit, have all gained the same potential energy, this bulk potential energy. Okay, now with the first law, when working with the first law, you'll also sometimes hear the term flow work. And this is primarily in reference to when mass is transferred into or out of a system, mass is transferred across the system boundary, and specifically mass in the fluid form, the liquid or gas form. So, for example, if you have a fluid, so a liquid or a gas flowing through a pipeline, let's say your system is some portion of the pipeline here. Well, okay, in order for this mass to enter or leave the control volume, which would be through these faces here of the control surface, the surrounding fluid outside of the control volume has to push fluid across the control surface into the control volume, or push fluid across the control surface out of the control volume. Because the fluid inside of the control volume is under a pressure. So you need to apply pressure to push mass into the system or to push mass out of the system. And so this pushing action requires energy. And this energy is what's called flow work. It's the pressure volume work required to push fluid, liquid or gas, into or out of the control volume. So when mass crosses a control surface, it carries energy that's associated with its internal energy, its kinetic energy, its potential energy, and its flow work. Okay, so now that we have a solid intuition for how the general first law works, let's think about how the first law is applied in the majority of cases when analyzing chemical reactions. So, how is the first law applied in chemistry to analyze the energy transfers and energy balance of chemical reactions? Well, okay, the idea is, so if you're scientifically analyzing a chemical reaction, and notice I said scientifically, so not just thermodynamically, but scientifically in general. Okay, well, when you're analyzing any problem in science, physics, or engineering, you're first going to define what your system is. And so if we're dealing with a chemical reaction, then in the majority of cases, the system is going to be defined to include all of the substances involved in the chemical reaction. So the system is such that it always encloses, it isolates from the surroundings, it isolates from the environment all of the reactant substances and all of the product substances. If the reaction hasn't started yet, then it's just isolated from the surroundings is all the reactant substances. If the reaction is ongoing, then the system is just isolating. It perfectly encloses the mixture of all remaining reactants and all products that have been produced. And then if the reaction has gone all the way to completion, then the system encloses all of the product substances. So the system contains all of the reactants and products involved in the reaction, and then the surroundings are everything else in the universe, with the system boundary being defined as a hypothetical boundary that always perfectly encloses all reactants and products, regardless of where they move, how the volume changes, or how the reaction proceeds. So conceptually, the boundary deforms, expands, contracts, and moves if necessary so that it always encloses all of the reactants and products involved in the reaction. All right. And so in this case, then, with this type of system definition, what you can notice is that these mass transfer terms are going to be zero because the system is always enclosing all reactants and products. It's not allowing any of the reactant or product substances to cross the boundary. All right. And this is what's called a closed system. A closed system has no mass transfer across the system boundary. And then an open system, on the other hand, allows mass to cross the system boundary. All right. And so for the majority of first law analyses of chemical reactions, the system is going to be closed, which we can see, therefore, means that the only types of energy transfers that can occur across the system boundary is heat and work. Okay, now also in most cases when analyzing chemical reactions, the changes in the bulk kinetic energy and potential energy, these two terms are going to be zero as well, right? Now, remember though, this is not saying, these two terms being zero is not saying that the entire system has no kinetic or potential energy. For example, so almost every system that you analyze on Earth is going to have at least some gravitational potential energy. If you're analyzing a chemical reaction that's occurring on a lab bench, well, that lab bench is above ground level, right? Okay, but what appears in the first law balance equation is the change in the potential energy. In this case, we're thinking about gravitational potential energy, but there's different forms of potential energy. But it's the change in potential energy over some time delta t. And so if the chemical reaction stays on the lab bench, then the delta PE, the delta gravitational potential energy, is zero. So when applying the first law to study chemical reactions, in the majority of cases, these two terms are going to be zero. And so what we're left with is delta U is equal to Q plus W. And so this is the reason why when working on or studying chemistry problems involving the first law, the default approach, which you'll see the majority of the time, is the first law is just strictly stated from the start this way. Okay, but now there's one more important point that we need to discuss. So you might be asking, what about enthalpy? You might have heard of enthalpy, and so you're wondering, isn't enthalpy a part of the first law? Okay, well, we're not going to talk about enthalpy in this video. You'll see exactly where enthalpy comes into play in an upcoming video. But so the last thing we want to do here is talk about this work transfer term W here, because you might be thinking, well, okay, in general chemistry, when analyzing strictly chemical reactions, won't this work term usually be zero as well, right? So, like, what forces, if you're just analyzing a chemical reaction, what forces are present at the control surface during the chemical reaction? I mean, yeah, you had the piston cylinder example. So in those cases, you have a chemical reaction, a combustion reaction occurring inside of a piston cylinder, and so you have forces occurring on the piston face. But again, like the general idea, if we're just strictly analyzing a chemical reaction, if you just have the environment enclosing some chemical reaction, then what forces are going to be present at the control surface? Won't the only type of energy transfer across the control surface be just Q? Well, no, actually. So even if we're purely just analyzing a chemical reaction, so the reaction is not taking place inside any kind of device or machine where it's pushing on something in order to move it. We're purely analyzing the reaction itself. Even in that case, so let's come back to the hydrogen displacement reaction here. So again, the idea is you start off with the system just encloses all of the solution. And then as the reaction proceeds, you've got hydrogen bubbling out, hydrogen gas bubbling out. So you get this hydrogen gas body. And so now the system, if the system is just enclosing all of the reactants and products, by the end of the reaction, the system has to expand out here to enclose all the hydrogen gas as well as the solution. Okay, and so going from the reactants to products, the system definitely expands in this case. The delta V of the system, if you calculate the volume of the system before the reaction has occurred and the volume of the system after the reaction has occurred, and so you subtract V2 minus V1, you're going to get some positive delta V. The system expands. Okay, well, in order for the system to expand, in order for this H2 gas specifically to expand into its final volume, it has to push the surrounding atmosphere out of the way. And in this process, this is work taking place at the system boundary. Specifically, this is a type of pressure volume work, often called PV work. And the determination of the magnitude of this PV work is often simple in many situations because atmospheric pressure is approximately constant for an entire chemical reaction, right? And so in that case, all you need to do is, to get the amount of work transfer, you just multiply this constant atmospheric pressure by the delta V. But it wouldn't be that big of a deal anyway if the pressure, say, weren't constant as the volume of the system was changing. In that case, you just need to get the pressure as a function of the volume, and then to get the work, you just integrate the pressure over the volume. And so if the volume increases, the volume of the system increases against an external pressure, then energy in the form of work is transferred out of the system. So in the first law energy balance, that's going to be it's going to be negative there's energy that left the system. If the volume decreases against an external pressure, then the energy in the form of work is transferred into the system. And so now you can see why, when analyzing a pure chemical reaction, if this system was enclosing just a pure chemical reaction, so it's not a chemical reaction that's inside of a piston cylinder or some type of engineering device or something, we still leave the work transfer term in the simplified first law equation by default, because a chemical reaction in most cases is going to be occurring in some sort of pressurized environment, like Earth's atmospheric pressure, or underwater in the ocean, let's say, or in the human body. But in some special cases, like in empty space, there is no surrounding pressure. In that case, there would be no PV work. And so this PV work is ultimately where enthalpy is going to come from. And again, we'll talk about enthalpy in an upcoming video.